Okay, I've got my scope set at 2 volt per division. So 1 square is 2, and this is a 10 to 1 probe, so it represents 2 volt 1 actual square. Now I'm going to apply voltage direct across my load and watch what actually happens. Okay, I'm just going to reset it and watch it now, what's happening. Watch it. Sorry, let me do it one more time. Okay. Now, if you look at it, basically, from here to over there, we got 1, 2, 3, 4, 5, 6, 6,5, 6,6 squares. Okay, 6,6 times 2, that gives me 6,6 times 2, that gives me basically approximately 13,2 volt, okay, which is my full supply across the actual load where I'm actually feeding. Now I'm gonna basically connect now the NTC. Okay, but before let me set it up here again on the front of the scope. Okay, and then you will see that at the beginning of the trace, it will be much smaller current, and along that current you bring down with the NTC to below 30% of the total voltage and current across the load. You actually protect the actual fuses and circuit breakers from blowing, and of course if using it as a protection of the relay contacts, you protect the relay contacts from arcing and melting on that inrush current. Alright, now as it resets now, basically you can see over there, okay, you can see over there. Alright, there we go. Now let me just display the waveform. Okay, now if you look at it, we got 1, 2, 3,7 at the beginning, because you can see now it's starting to go up because NTC starts heating up. So you're looking about 3,5 sort of times 2. So 3,5 times 2, that gives us about 7 volt. So we have reduced it from 13, something volt down to 7 volt. Or we have reduced it, if you look at it over here, let me just do this and connect the, and you'll actually see it even on the amp meter, from 8,9 ampere. Now I've got it with the, I'm going through the NTC, okay? So if you actually look at it, you will actually see, okay, I'm going only 4 ampere. 4 ampere, and now look at it there, it's going higher and higher because the NTC is getting hot, and in turn actually it lowers the resistance till it reaches a certain temperature and then lets a full current go through. So in a nutshell, that's what basically, let's do it again. I have demonstrated what the actual NTC, which you get it in different currents for different sort of wattage loads and things like that. So whether it's AC or DC, and of course sometimes one requires but more sort of delay or to lessen the arc across the relay or whatever. Whether it's a this or whether it's a this size, it doesn't matter what size. Yes, you can along there the same part number or same value NTCs. Yes, you can connect them in series, and in turn you will sort of increase the actual delay. You will lower the current, but you will increase the what you call it, the actual delay time of the inrush current, and that's what's actually wanted. 99 times out of 100 with one device you get away, but there is special applications where you must stack them and put them in series. In parallel you cannot do them. The reason why, because not both of them one will switch on faster than the other, and the temperature one will become much hotter than the other one, and being hotter, it will actually not evenly distribute the current going through both. So you do not use NTCs in parallel, only in series. I'm talking about the NTCs for the inrush current, the ones that we're talking about. On that note, I hope you understood what I was saying. And it's a very complex subject, but this is basically what this thing actually does. NTC for the inrush current. Thank you. On that note, from Batos Radio and TV.